Hi, my name is Matt Steinborn, and today I want to talk to you guys about quantum computation, some QFT-based arithmetic algorithms, and the implications of both these things. So to start out with, I just want to give some background about myself. I am a firmware engineering consultant by day, so I live in the embedded world most of the time, but by night I'm getting a master's degree in computer engineering with a focus on computer architecture from Tufts. The reason why I'm interested in this topic is because quantum computation is computer architecture. Just like we talk about hardware accelerators, GPUs, micro-architectural optimizations, quantum computation represents a new field that will allow for new problem-solving techniques in the broader field of computation. Right now, ACM will accept papers on this subject, meaning it falls within this category. So to start off with, I wanted to give you guys a little bit of background on quantum computation. Now, unfortunately, we don't have the time to do a full deep dive, but the one thing I wanted to dispel right out of the gate is that quantum computers aren't just faster computers. They're a specific piece of hardware that leverages the properties of quantum mechanics to solve specifically designed algorithms. They don't just run normal programs faster. I hear that parroted a lot, and it's completely false. What they can do is they can use quantum interference, entanglement, and they can solve a very niche set of problems. The interaction on the left is important, the interaction here, because that's more or less how, at least in the short term, we envision the quantum computation working, and that the classical computer is still in charge of control logic, and this performs almost like a subroutine. So what are the implications of quantum computers? Well, many of you maybe heard about quantum cryptography and the fact that many of our public key cryptographic systems are going to be broken sometime in the future. This is because there's an algorithm known as Shor's algorithm that can determine two prime factors of one large number in exponentially faster time than a classical computer. Another proposed method to use quantum computers is quantum communication, wherein you have, through entanglement, two qubits that are both encode information that you require both to decode an original message. People are determining new use cases all the time. This is still a very new frontier. Now we could talk about what this project aims to accomplish. And specifically, what I'd like to do is take a quantum algorithm that's been proposed in literature, implement it in a high-level programming language, test and simulate that it works correctly, and then use what is known as a resource estimator to contextualize what the hardware requirements for this is. With all that out of the way, we can generate some takeaways, broadly speaking, about what these algorithms mean and can we implement them. Now, last little bit of background. Sorry for anybody who's not math-minded here, but I wanted to talk briefly about the Fourier transform. Think about it as a way of it's a mathematical operation that lets you look at a frequency that is normally in the time domain, as you've probably seen most signals, and instead place it in the frequency domain. So this image does a really good job capturing it, in that you can see that we have what is basically the summation of three sinusoids. And when we take the Fourier transform, we can see the frequency of these three sinusoids here. There is a quantum parallel to this operation known as the quantum Fourier transform, or the QFT. See, this operation here in the bottom left is the discrete Fourier transform, which is the digital version of the Fourier transform. Through these rotation gates, R2, R3, R4, we're able to take a register of qubits, basically a bus of qubits, so to speak, an array of them, and rotate them based on their position. In doing so, we can reconstruct this series in a quantum register. What we're going to be looking at today are ways of doing algorithms that when you take the quantum Fourier transform, do this algorithm, and then undo the quantum Fourier transform, you get back basic arithmetic operations. Specifically, we're going to implement Draper's adder, which when you take the quantum Fourier transform, you can apply a series of rotation gates based on a separate number. Then when you undo the quantum Fourier transform, you get the original number and the second number added together. Why is this relevant at all? Well, I already mentioned that the QFT is a natural part, I shouldn't say natural, but is a common part of a lot of quantum algorithms. And so if we can have an intermediate operation that when we decode, when we reconstruct our quantum register as it was before we took the QFT, we can have two numbers added together. This also uses fewer qubits, which is a really big deal because we're in what is known as the NISQ era, or the noisy intermediate stage quantum era. What all those words mean is basically we have very few qubits on our quantum computers and they're all noisy as hell. So using fewer qubits, it means fewer vectors for noise injection And we can maybe implement this. By virtue of just having an adder, if you can think about arithmetic, we have a subtractor through what is known as the adjoint, which is like the inverse of our operation. We also have multiplication, because if we just sum n times, we get n times our original number. And then if we just add our multiply operations, we get a weighted sum. Okay, so mention the algorithms I want to implement. How are we going to do it? Okay, well, there exists what are known as high-level programming languages. The same way you would take a compiled language like C, C++, and run a compiler, and it would give you an output binary, you can write your high-level quantum program, which in my case is written in Q#, run a quantum compiler, and it'll generate basically a recipe list of the quantum gates we want to perform and when we want to perform them. I'm a visual guy. Instead of telling you about code I wrote, I'd rather just show you the code I wrote. So we're going to jump over to Azure's portal, which is Microsoft's coding platform. And some of you might already have noticed that this looks just like a Jupyter notebook, if you're familiar with that. And that's exactly what we're using here. Our Q# is just used through a wrapper in Python. You can see we have a number of operations which work much like functions and other programming languages, except these are quantum operations. And you can see we have one to prepare a qubit for our addition, the addition itself, which if you looked at the figure on the last page, you can see all of our rotations done iteratively through nested loops. And you can see our two QFT operations, like I promised you. We can just go ahead and simulate the different quantum operations, and it'll generate the expected outputs. So here you can see that, okay, these all check out. 3 + 3 = 6, 4 + 3, whatever. I'll spare you the details. What's interesting, though, is we also get seemingly incorrect answers at first. 7 + 4 is not 3, but you have to remember that we have to specify the number of qubits we're passing. So we actually get 7 + 4 is 11. So we get 3 mod 8. So 3 + 8 is 11. So it's 3 modulo 8 is our actual answer. And that's a facet of Draper's implementation, is you actually get the modulo. If it overflows the qubit register, it actually just becomes modulo the number of qubits you have. So the number you get back modulo, that's your answer. Or we can just run the adjoint or inverse of our adder. So here you can see the same exact logic, we just have this word adjoint in front, and we get subtraction. And again, we simulate, and you can see 16 minus 5, yeah, it's 11, 6 minus 5 is 5, yeah, this all looks good, this all looks right. Do some multiplication. And if you think about it, A times n is just A added together n times. So that's basically what this operation does. We can see that when we simulate this, we get 10 times 5, 50, 60, 70, that all looks good. And then just like our addition operation, we will get the answer modulo the number of qubits we have. Now, I mentioned briefly that we have a tool available to us also called the resource estimator. The resource estimator relies on a fault-tolerant implementation. So you can see we have 209,000 qubits, but when we actually kick the tires on it, we have 6,000 physical qubits. What we also have are these 203,000 fault-tolerant qubit, basically, that isn't really within the purview of our current scale of quantum hardware, so I neglected these, or I eschewed them in my analysis here. With that in mind, I compiled these results. Let's jump back on the slides and we can talk about them. Welcome back to SlideLand. Let's talk about what the resource estimator gave us. So, like I was saying before, the resource estimator, how it works is you give it some input parameters, your error tolerance and the parameters of your qubit, and it will give you what your target's requirements will be for your algorithm. We're only looking at error correction qubits. Error correction, if you saw on the resource estimator, you saw it told you how many logical qubits you needed and how many physical qubits. Basically, because qubits are so noisy, you actually need a larger number of them to represent one. There are a number of mitigation techniques. We're not really going to talk about that, but just know that we need a large number of qubits to represent one qubit. So how did we do? Well, our Draper adder, we needed 6,000 qubits. Our multiplier, we needed 8,450. The operation times are important to note too, 750 microseconds and 2.7 milliseconds respectively. Our weighted sum, I didn't implement it, but we can just do the math, right? Suppose we have 5 values, 5 product pairs. We would get around 73,000 qubits. Those are just numbers. How do we contextualize it? Well, we can look at the hardware that is available to us. So Azure's portal does let us submit to real quantum targets, and these are 2 of the options. We have Rigetti's Aspen M2 and M3. They're lumped together because they're very similar. They have about 80 qubits, one's 79, one's 80, and they have a coherence time of around 24.2 microseconds. We also have ion-Q's harmony, which only has 21 qubits, but those 21 are not equal to those 80. Those 21 are much, much better in terms of error rates. They also have a much larger coherence time. So we could conceivably maybe perform some of these operations provided enough qubits. We don't have enough qubits, but if we did, maybe we could do it. I wanted to go a step further and just illustrate something about how noisy this hardware actually is. So on the right, there's a circuit implementation. It's not too important. What you need to know is that this is a circuit that detects quantum errors. This detects errors in your bits here, your qubits. So when we simulate it, we expect a deterministic result of 0, 0 every single time we run it. When we ran on actual hardware, we actually got a histogram of values, a probability density, where we actually only got the right answer 44% of the time. Now this is a circuit to detect errors, and we are introducing error. So quantum hardware is still in its infancy. Not only do we not have the qubits, and we don't have the coherence time we need, we also introduce error when we're trying to prevent it. So we're in a tough spot. So what can myself, having done this, and you, the viewer, take away from what has been done? Like I said, quantum computers aren't just faster computers. They are about using quantum mechanics to generate these algorithms that can solve challenging problems. On the right, I have a series of truth tables. Underneath, I have a single, how you might represent one quantum register. You can represent them as a summation of all the possible values. If you can, this is a little hand wavy, but if you can take a step back, you can look at something like an AND gate here, where we have 4 possible values. With quantum computation, we can represent all 4 of those values in one state. We could just have 4 different parameters that represent with equal probability each of these states. So you can see how, as we compound our quantum algorithm, we are actually able to encode more information using qubits than classical bits. I also wanted to get across that this quantum hardware is real. The tools to use it are real. I showed you an output from a real quantum target, Rigetti's Aspen M2. You can right now log on to Azure's portal and write quantum programs yourself, and I really encourage you to do it. To note that there's not a lot of business and personal use cases for it, but it's great for research. It's great for learning about quantum hardware. And finally, what have I, not the viewer, learned? Well, testing these algorithms is hard. There's not a lot of great ways to determine your intermediate outputs and determine why exactly you're not getting what you want. Because quantum states, when you run it, if it's not prepared correctly, or even sometimes by design, you don't get the same answer every single time. You get a probability density of answers. Figuring out why my algorithms weren't working was a big challenge. There is still a challenge in actually proving to people why quantum hardware is valuable. You can reference things like Shor's, but a lot of the value is still derived from theory and potential algorithm design. We can't implement Shor's on a real quantum computer. We can't even implement an adder. We would love to have real quantum algorithms that we could run on real hardware, but that's just not where we are right now. But finally, the biggest takeaway is that of all these limitations I mentioned, only a fool would take those and say, write off quantum computation entirely. It still represents a brand new frontier. An exponential speed up on some of our classical algorithms is nothing to scoff at. You see companies, they would kill to have a 2-time speed up. So an exponential speed up, that's a big deal. Thank you for your time, and I hope you got something out of watching this video.